two ways to write it. So the first one, call it G1. I have just the identity, E. I'll take something, I guess I'll call tau1, and I'll define it as follows. It'll take one to 2 and 2 back to 1. And it'll also exchange 3 and 4. Tau2 I'll take to be something that exchanges 1 and 3 and 2 and 4. So 1 goes to 3, 3 goes to 1, 2 goes to 4, 4 goes to 2. Is that clear? And the final element I'll take is tau1, tau2. And just by tracing through these things, so first I look at what tau2 goes to 1, does to 1, say. So tau2 takes 1 to 3, and then tau1 takes 3 to 4. So 1 goes to 4. And if I just keep on computing these things this way, I find that 4 goes back to 1, 2 goes to 3, 3 goes to 2. But it's also easy to verify that if I reverse the order, if I take tau1, if I apply tau1 to something and then tau2 to the result of that, then I get exactly the same thing. So just a sort of linguistic point here. We say that these things commute. Tau1 and tau2 commute because tau1, tau2 equals tau2, tau1. So what is the group structure here? Well, what's tau1 squared? It's the identity. What's tau2 squared? What's tau1, tau2 squared? Exactly. So the group structure is very, very simple. Each of these things, if we multiply by itself, you get E. Obviously, if you take E by any of these things, you get whatever you multiplied by back. And if I multiply tau1 by tau2, I get tau1, tau2, or tau2 by tau1, I get the same thing. What about if I multiply tau1 by tau1, tau2? Exactly. So if I take any of these things of order 2 and I multiply them by each other, I get the third. So here's another way of writing the group. I could just write it as the set of matrices. So in GL2R, say, I could just write it as the set of matrices, well, identity matrix. Where I just change the entries here to minus 1s. So certainly these have the same relevant property. If I multiply any of these things by themselves, I get the identity matrix back. And if I multiply any two of the things which have negative entries, then I get the third of the things that have negative entries. So again, they have the same multiplication table, and there's a nice direct bijection. I can, for instance, have the bijection F take E, so I could define F, and it would take E to the identity tau1 to this, tau2 to this, and tau1, tau2 to this. Do I really need to include tau1, tau2 in this list? Well, yes and no. If I wanted to say, just consider the group, the smallest group that contains tau1 and tau2, well, I could have just said tau1, tau2. But if I want to write out the entire group explicitly, all of the elements, then I need to include tau1, tau2, and the identity.